All right, let's get started. So we will start out without jumping to the presentation. We'll start out with the basis of the determination of why we're doing this particular topic, which is the root locus approach. And locus is a mathematical term, which is basically a trajectory of a direction of how a root is changing. You are plotting those different roots as they change. And so the locus is really just a plot of all the roots. And if you recall from last semester, I had this mantra. I said, you start at a pole and end at a zero. And we'll see why that's significant, because we'll look at our typical, very simple block diagram where we have an input. We have a feed forward gain G, our output, and then we'll feed that back through our gain block H, and then we will have our plus minus in that direction. And if you remember the closed loop transfer function for that, our output over our input is going to be equal to G over 1 plus GH. That's the basis for the root locus, because what root locus says is, what if we were to insert a proportional gain block? And this is a constant. It's a real constant. It's not complex. It doesn't have a magnitude or an angle. It just has a number. Okay. And if we add that in, we're going to modify our closed loop transfer function just a tiny, tiny bit with our K term as shown that way. Okay. So if we look at this and we recall that our G has, a numerator and a denominator, and our H has a numerator and a denominator, then we'll go ahead and rewrite this as over GD all over 1 plus K GN HN over GT HD. And then we're going to put that under a common denominator, invert and multiply, yada, yada, yada. So what we end up having is K HD GN all over GD HD plus K GN HN, correct? If you remember from our work that we've done. So now we're going to allow K to vary. So K, we're going to start it at 0. So K is going to be greater than or equal to 0. And it'll be less than or equal to infinity. So what we want to do is we want to take a look when K is very, very small. And we're only going to focus here on the denominator. And the reason why we focus on the denominator is this is our characteristic equation. So if we get the roots of our characteristic equation, then what we can see, or what we can say, is that we have, hold on, I'll just shut the door real quick. All right, sorry about that. So our roots of our characteristic equation are what determine the performance or the operating characteristics of our particular system. So all we need is the roots of our characteristic equation to tell us how the system is going to respond, whether it's going to be stable or not, how fast it's going to reach steady state, how much overshoot, et cetera, et cetera. So our roots, our characteristic equation of our roots, is really what we're looking. We'll look if K is equal to 0. So when K is equal to 0, we have GD-HD is our characteristic equation, and we need the roots of GD and HD, correct? Well, these are the original poles of our system, because these are the denominator terms. Those are the terms that were originally in our value. So when K is a very small value, then all we're going to have is the poles of our original system. Remember the poles of our system, if we had a transfer function, we had zeros and we had poles. So when K is equal to 0, we're just going to end up with the poles. There's no numerator terms that are going to influence any of those poles. What happens as K approaches infinity? Well, these two terms have almost a negligible effect on it. So when the K approaches infinity, what we're going to end up with essentially is Gn times Hn, and those are the zeros of our original system. So when K goes from 0 to infinity, we're going to start at the poles, and we're going to end at the zeros. So if you recall when we did pole zero maps, when we said how many finite poles are there and how many finite zeros are there, and if there's any discrepancy between the two, we would end up having the infinite poles or infinite zeros, and they would always be the same. So if we did a pole zero map, and let's just pick a random one, let's say we have a pole over here, a couple poles over here, and a 0 over here. This one has 3 finite poles and 1 finite 0. But the idea is that this has an order. When we look at the numerator and the denominator, it's going to have an s cubed and an s to the 1 in the numerator. So s cubed over s1. As we take the limit, as s approaches infinity, infinity, what we end up seeing is we have 1, I should say, over s squared, which means we have 2 infinite zeros. Because as s approaches infinity, we end up with 2 more zeros, right? Because we have 1 over infinity times infinity. Those approach 0. So we have that value. So we actually have a couple of zeros someplace out in the system, which is very important to us, because if we're plotting a root locus, and remember, the root locus is how we start and stop as K goes from 0 to infinity. We're going to start at a pole, and then we're going to venture until we end at a 0. We're going to start at a pole and end at a 0. Start at a pole and end at a 0. So the idea between having those infinite poles and zeros is really so that we can make our root locus plots work out for us. We have to have 3 roots or three poles, which means we have 3 root loci. So one of the rules that we have is the number of branches or loci. This is just a, don't worry too much about the mathematical term, is equal to the number of poles. Okay. So when we do the root locus approach, we have a lot of equations to do, and we have a lot of rules to do. But if you start off by saying or recognizing some of these rules, like this mantra, start at a pole, end at a 0, it's going to really help you understand how to draw in the directions of things. So that's kind of the precursor to how I wanted to make sure everybody was on sort of the same page in terms of understanding the basis for root locus and how we go ahead and get it set up. So questions on this sort of initial discussion? Everybody understands sort of the motivation of what we're trying to do. We're trying to see as K increases, we want to look and see what happens. And again, because we're trying to look at the performance of a system, we want a system that might have a certain percentage overshoot, or we might have a system that we wanted to have a certain rise time or a settling time, which means maybe we need a route or the routes that can't be any further than that location. So if these are, let me change the color here. So we want routes that can't exceed the real part being greater than that point. So this could be a bounding condition. And we would have to say that our value of K can't exceed that value. So we can use our root locus to come up with a bunch of plots to go ahead and figure out what do those values of K need to be. Similarly to what we did when we did our Routh-Hurwitz approach to solving for ranges of K that resulted in a stable system. So that ultimately is what root locus is going to do for us. Questions on that? All right, the last thing that I will add is let's look back at this denominator again. 1 plus K G times H. And these are both functions of S. Now, if we want this to have a valid root, which means whatever value of K we apply, we don't know what K is, but it's a real number. So whatever value of K we applied, it has to be a valid root. So for a valid root, we require that 1 plus K times G of S, H of S, by definition, has to equal 0, doesn't it? If it's a root, 1 plus K times G, it has to equal 0. That's the definition of a root. When you plug in a value of S, you know, whatever S is going to be, if it's a valid number or a valid root, this term will equal 0. So you can use this concept, or you can use this idea for helping you identify or define root locus, because you know that the criteria of 1 plus K GH has to equal 0. And then what that allows you to do is, you know that my magnitude, so let's see, so K G H equals -1. And let's see, so K equals -1 over G times H. Now, G times H, we can plug in values of S, right? So this to be a valid root. So if we recall, S can be a complex number. So we know that the magnitude of K is going to be equal to +1 over GH magnitude. And the angle of K is going to have to be equal to plus or minus 180 because of that value there. And actually, excuse me. And actually, we can expand that, because what we can say is the angle of GH has to equal plus or minus 180. And the reason why we can say that is K is purely a real number. Okay, so K isn't going to change anything in terms of the angle. It's only going to affect the magnitude. So we really can use this to figure out breakaway points, break-in points. We can do all these calculations because we know we have to equal that plus or minus 180 degrees. So we're going to use these concepts to go ahead and start to come up with some definitions, some variables, whatever you want to call it, to go ahead and define our rules for our root locus. Okay, so that's what I wanted to get to before we jump into root locus, because I think it's always really useful to tie in, you know, kind of what we're talking about and why all this stuff works. Well, it works because we're going back to our characteristic equation and we're setting it equal to 0. If it's a valid root, then we're going to get good results. All right, so root locus. So it's a graphical approach. That's all it is. It determines all possible closed loop pole equations, right? Or pole locations. Pole meaning it's a valid a root that's in the denominator. And this is all possible closed loop locations as my value of K is increased. That's why it's a one parameter controller design. The only thing that we're allowed to change is that gain block that's in there. So that's why it's just one parameter. So here is a block diagram that's been, or a system that has been converted into a simplified, block diagram. And its transfer function. So we basically have done the math so that you've got this K value in here. And you can see if K is equal to 0, your roots are going to look at a very different location than if K is equal to 56 or 106 or whatever. So we want to have some intelligence associated with that so that we can draw our value of K without, draw our root locus plots without actually having to calculate the roots for every single value of K. Okay. All right. Let's start out with K equals 0. K is equal to 0. So we're going to substitute in to our characteristic equation over here. So now we end up with S cubed plus 4S squared plus K times S, which in this case is 0, S plus 1. So can you tell me about this particular characteristic equation? Is there any information about that you know, based on looking at this, that will help you determine anything about its stability? Anything relevant here or useful? There's one little piece of information that we can glean about its stability just by looking at this basic characteristic equation. Anybody want to guess? How about Sean? Do you have an idea? Can people hear me? Am I coming across? Is my audio okay? Oh, that's not good. Can anybody hear me? Moses, am I coming through?
Yes.
Oh, okay.
Yeah.
But I'm sorry to pick on you again, but can you tell me anything about the stability, Moses, just by looking at this characteristic equation? Not doing any more work.
So what I can say is like there should not be any change in the first column to state that the system is stable.
That's what Ruther Hurwitz would say. So yes, that's the rule about Ruth Hurwitz. How about this? Do I even need to do Ruth Hurwitz to comment on its stability?
That 0 on S makes me think. Is that going to play any role?
Yeah, that's exactly right. Remember the necessary but insufficient conditions for a stable system? One of those is that no coefficient vanishes. There's no 0 term. So if we have a 0 here, this system is going to be unstable, right? And if you look, take a peek here, we can see that minus 4.06, that's a root that lives in the left-hand half plane. So that doesn't affect stability. These two, 0.03 plus or minus J.5, those are both in the right-hand half plane because those closed loop poles are positive numbers. And I didn't even need to look at this to know that I had an unstable system, that I know I had at least one pole in the right-hand half plane because I saw a 0 here. So the first thing I can say is that 0 is going to make an unstable system. But I'm going to start off with my plots or my values, and I'm going to go ahead and I'm going to see that that's the value. Now, K equals 0. So this K equals 0, this is the original equation that I have. S cubed plus 4S squared plus 1. Now I'm going to add in my K equals 1. So these are the original poles of my system. This is where I start. I'm starting at minus 4.6 and 0.03 plus or minus J.5. Now I'm going to increase my value of K. So I plug in my value of K equal 1. Now I run through the plug in my roots in MATLAB. and I get minus 3.81 and minus 0.1 plus or minus J.5. I continue, I go to 2. What do I get for 2? I get minus 3.51 and minus 0.24 plus or minus J.47. So you can see that I'm starting at these and I'm starting to go away from them. And I don't necessarily know which direction I'm going, but I'm moving away from my values. Continue on. Here's my 3, minus 3.15, and I have my values here. Minus 0.43 plus or minus J.37. And I think this is the last one I did, putting in a value of 4, minus 2.62, and minus 1, minus 0.38. So interestingly enough, these over here start away from the J omega axis, or start off the real axis, and eventually get on to the real axis. And then this is interesting because now this pole moves away from the J omega, the real axis, and this pole does too. And now this goes over here. Now it's very important to note that you still always have to have complex conjugate pairs here, right? You can see that these are still complex conjugate pairs. So this is what we're trying to do. We're trying to guess the behavior of how these roots will continue to change based on the fact that we're increasing our value of K. That's all that we've done here. And you can see K here is a real number, 0, 1, 2, 3, 4, all the way up to 5. All right. And then you can see the plotting of the poles. We started off at minus 4.06. We started heading in this direction. And then over here, we had plus or minus 0.03, plus 0.03. So wait a minute, where are you? Minus J.5. So that's those two right here. And then we started walking in this direction here and here until we ended up getting onto this, back to this real axis. And then eventually we walked away from the real axis as well. We'll actually be able to come up with a way of determining what this looks like once we start to implement some of this work. Nope, sorry about that. So you'll actually see those moving this way. Okay, so you can see as you increase K, your pole that's on your real axis is moving to the right. Your other two poles are moving to the left. And this is what you want, because as I increase K, I get an unstable system. Now, if we look at that again, think about the concept of starting at a pole and ending at a 0. So take a look where it starts. It starts out at a bunch of poles, and then it's going to start walking closer and closer until they get to zeros. And see if you can notice where you have a bunch of poles or zeros at s equals infinity. So walking towards each other. So it's hard to see, but you actually had, over time, these two would approach infinity, and this one would start to go over to the right and also approach infinity, because you have 3 poles, which means you have to have 3 zeros. So let's do this structured approach. So we'll start off with this. Excuse me, this second order transfer function. And we know that it has, if it's underdamped, overdamped, or critically damped, it doesn't matter. We just use our generic equation, s squared plus 2 zeta omega sub ns plus omega sub n squared. We're going to use our quadratic equation to come up with the poles. So here's our base equation, negative zeta omega sub n plus or minus j omega sub n times 1 minus zeta squared. Don't forget, we defined our damped natural frequency as this term here, so we can make that substitution just to simplify it down a little bit. So now, let me get this out of the way so I can see it. So now we're going to look at, again, this is just kind of a rehash from looking at our second order systems. We have our real part is defined by zeta omega sub n. This is how far away it is. And then our imaginary part is defined by omega sub d. How come it's not moving? Okay, these are always complex conjugate pairs. By the way, what is the line of a constant settling time? Anybody remember? Remember your equations for second order systems and settling time? Remember the 2% settling time was 4 over, I believe it was zeta omega sub n. So that would be your constant settling time equation, right? So zeta omega sub n has to be constant. So this would be that constant settling time, which makes sense because if you recall, this is going to be an alpha term, whatever that value is. And then if we go back into the time domain, we have e to the minus alpha t. If this term never changes here, if it always stays at that point, 5 time constants is going to reach our, well, almost 5 time constants is going to reach our 2% settling time, which means we're going to get a constant time as to how it decays away. So this is a constant settling time. What about what is the constant with zeta? So zeta, if you remember, let me erase some stuff. We'll do a little bit of trig identities here. So if you recall from zeta, the inverse cosine of zeta gives you that value of theta. So this line right here, that blue line tells you the constant damping that we have, okay? So it would always stay at 0.707 or whatever value you have. What about omega sub d? If that's constant, then you're going to have a constant imaginary term. So your damped frequency is going to stay the same. So you're always going to have an oscillatory response that is this omega sub d then. Okay. What about omega sub n? Omega sub n is that term there. Does everybody remember how we got those terms? Let's do the trig identities because it's quiet and you might have forgotten these terms. So let's go ahead and define this. All right, so let's draw a right triangle over here. Like that. And that. And this value is omega sub d. And this value is zeta omega sub n. Don't forget, omega sub d is equal to omega sub n times 1 minus zeta squared. That's our definition. This equation over here, this is the hypotenuse. So that hypotenuse is going to be pi zeta omega sub n, that term squared, plus this term squared, plus omega sub n times 1 minus zeta squared, that whole thing squared, square rooted, okay? So let's see, we have the square root of zeta. I gotta have the squared term over here, squared omega, omega sub n, I started to write zeta, sorry about that. Omega sub n squared plus omega sub n squared times 1 minus zeta squared. This term here and this term will cancel. So what I'm left with is omega sub n squared, square rooted, which is omega sub n. So my hypotenuse here is omega sub n, okay? That's how I solved for that term. Now I'm going to use a trig identity. What does SOHCAHTOA say about theta? What does SOHCAHTOA say about theta? How do I solve for theta? I know that this is omega sub d. This, the real axis is minus zeta omega sub n. And the hypotenuse is omega sub n. So how do I solve for theta as a function of the sides of my triangle? Anybody? This isn't a hard question.
Sakatoa.
Sakatoa, yeah. What is, how would you write the equation for this one?
Well, you know all three sides, so you could do any of them.
Yep, so which one should we do to solve for it?
Cosine.
Yeah, the theta, or the cosine of theta, is equal to,
It's opposite over
adjacent-
hypotenuse.
what's that?
It's adjacent over hypotenuse, right?
Adjacent over hypotenuse, yeah. So the adjacent is just a length, zeta omega sub n, divided by the hypotenuse is omega sub n. So this is zeta, correct? So the cosine of zeta, or cosine of theta, is equal to zeta. That's why this angle, if it's constant here, so if this angle is constant, that's how we end up with that term. So if we want a constant damping coefficient, then the inverse cosine of zeta is equal to theta. If this is a constant number, then theta is also going to be constant. So we can see why that value of theta, it's not going to continue to increase. It stays the same. That's why we have this rule over here. Right? I just want to kind of re-stress that because it had been perhaps long enough since we looked at second order systems that we wanted to see this triangle so that we can go ahead and build it. The first one, hopefully it makes sense because we did the e to the minus alpha t over here. That's why this one was over here. And again, if this one's constant, if omega d is constant, we're going to have a constant frequency that's not going to vary. All right, so what about the line of constant omega sub n? So if omega sub n is constant, then our radius is going to be constant. And what that's going to do is we can see how we're either going to have a completely undamped system up over here, or we're going to achieve a critically damping value at that point. So that is our constant value. That's our constant radius. But our damping can change and our omega sub d can change. We'll just swing between no damping and critically damping. Okay. And the line of constant tau, again, if the time constant is going to, the settling time is going to be constant, then our tau has to value. It just becomes 1 over zeta omega sub n. Because if we put, I'm getting cramped for space over here. So remember when we do the time domain stuff, 1 over s plus alpha in the time domain is e to the minus alpha t. And from a time constant perspective, e to the minus t over tau has to be the same as e to the minus alpha t. So if we take the natural log of both sides and divide out our t's, what we end up having is minus 1 over tau is equal to minus alpha. So alpha is equal to, or sorry, tau is equal to 1 over alpha. Okay? That's the approach that we would use there. Okay. Let's keep going. So what about the line of constant percent overshoot? What do we have or what do we know about that? It's got to be zeta, because zeta is the damping coefficient term. And again, that is only, if you remember our percent overshoot equation, that was only dependent upon our value of zeta. So if you don't change zeta, then your percent overshoot is not going to change. So if you want a constant percent overshoot, you're going to stay with that value of theta as shown there. All right, so we got to do a little bit of magnitude and phase. And before we jump into this, do you all remember how to do complex math in polar coordinates? Pretty important that we understand how to do polar coordinates so that we can get complex math, because if we don't get it, we can really struggle. Does everybody remember that? Let's say that A, let's do a little, I'll give you a couple minutes. Don't use your calculators. What is A times B equal to? I'll give you 1 minute to give me what A times B is equal to. Jacob, do you know what A times B is equal to? Can everybody hear me still?
I can hear you.
All right, thanks, Tom. Tom, do you know what A times B is in polar coordinates?
Not off the top of my head. I'm a little rusty with this.
Okay. Well, let me ask a general question, because this will kind of govern a little bit of the tack that I take for doing root locus. How much or where were you exposed to rectangular and polar coordinates, and how to do math in that? Has anybody done the math other than just entering it in your calculator?
I think I did a little bit in physics, but most of it in EET has been plugging into a calculator.
So,
Yeah.
so can you tell me a little bit more about what you were doing in physics?
I think it was physics 2, doing circuits.
So what do you remember about how you were presented with the math? I'm not picking on you, I'm just trying to understand.
No, if I remember right, we converted them back into rectangular numbers and added them like that. Again, that was a while ago.
Okay,
Hey Paul,
Anybody else?
would you multiply the magnitude and just add the degrees or phase like
yeah,
angles?
that's exactly right. So when you do polar math, okay, so let's break it down a little bit more. This is an XY axis, correct? So XY is Cartesian. Okay. And if we're doing with 2 dimensions, it's much easier to work. Well, I shouldn't say much easier. You can work in either Cartesian coordinates or polar coordinates. You could actually work in spherical coordinates, which is another coordinate system, but we don't necessarily have a lot of value to it. So for electrical engineers, we only talk about things from a real and reactive perspective, or the X and the Y axis, X being the real axis, Y being the imaginary axis. So what we want to do is we have to work with things vectors, right? In AC circuit analysis, we have a magnitude and an angle. We don't have purely magnitude or angle. Excuse me. So what we need to do is we need to work with vectors. So let's say that we have a 3 plus J 4 ohm resistor, okay? So we can represent that in rectangular coordinates. So we're going to go 3 in the real direction, and we're going to go 4 in the imaginary direction. And the corresponding vector that we have here is our impedance vector, Z. Okay? So Z, or the impedance of whatever circuit or element or whatever we're trying to find, is going to have 3 plus J4. 3 in the X direction, 4 in the Y direction. And that's how we get the vector Z. The other way that we can get the vector Z, at least from from a simplified electrical perspective, is let's do everything in polar coordinates. And polar coordinates assumes everything is a circle, okay? So it has a specific length, and that length is the radius, okay? That's the length of the circle or the polar quantity. And we can increase it or decrease the magnitude or the diameter of the radius of the circle just by increasing it or decreasing it. But the problem is that gives us this magnitude of a circle. What I'm really interested in is getting to the same point because this vector terminates at that particular location. So if I wanted to get to 3, 4, here, I can draw a circle, okay, whose radius is going to be equal to Z. That's the first part. And I know how to get the radius equal to Z. I can use, not Pythagorean theorem, but I can use, Pythagorean theorem. Geez, I can't think because I'm coughing all the time. 3 squared plus 4 squared is the magnitude of that term, all right? Now, the next thing I need to know is I can have the magnitude, but I've got to figure out how much to rotate around this circle so that I end up at that point. So the next thing I need is an angle theta. And my theta term is going to be found using my trig identities, which is going to be equal to SOHCAHTOA. So the tangent of theta is going to be equal to the opposite over the adjacent. This is the opposite, and this is the adjacent. So that's going to be equal to the imaginary term over the real term, or 4, delete that, or 4 over 3. Okay? So to solve for my angle is going to be the inverse tangent of 4 over 3. So to do any of the math, when I'm giving you, like if I'm giving you an AC circuits, I'm giving you 120 volts at an angle of 35 degrees. I know that the length of that vector is 120, and it's been rotated 35 degrees. But if I want to solve for the real part and the imaginary part, I've got to do a little bit of work. So how do you solve for the real part of that? How do I solve for the real part? Jacob, can you hear me now? Okay. Well, the real part is just SOHCAHTOA again, isn't it? I know the hypotenuse, and I know the angle. So to get the real part, so the sine is the opposite over the hypotenuse. I don't want that one. The cosine is the adjacent over the hypotenuse. So I want the adjacent over the hypotenuse, right? So the real part can be found by taking the cosine of the angle and multiplying it by 120 degrees. If I want to get the imaginary part,
You do the
I
same
think
thing,
the-
but to sine, right?
sine of 35 degrees, and multiply that by that same magnitude. And so to go from rectangular to polar, a real plus jx is going to be equal to the magnitude at an angle of theta, call it z. You should be able to go backwards and forwards. And we ended up saying this is Euler's identity. That's going to be equal to the magnitude times the cosine of theta z plus j sine theta z. That Euler's identity is just based on the fact that this is a right triangle and I can go ahead and build that. Okay, so that is the basis for using polar or rectangular coordinates. You're just writing a vector and you're writing it that's more convenient. I can tell you with 100% certainty, when you get into the real world, if you can do anything with AC systems, you have to be able to do rectangular, because all circuits that I've ever seen have a resistance and a reactance, okay? Some powers that I've seen have a P plus a JQ. You have to be able to also do polar coordinates because every voltage has a magnitude and an angle. Every current has a magnitude and an angle, but the way that you get the angle is, remember, it has 400 amps at a lagging 0.2 or 0.8 power factor. You should be able to get that theta I that way. Sometimes power is 100 MVA at an angle, a 0.8 lagging power factor. So if you do anything with circuit analysis, you're going to have to be able to do both and be very comfortable with those, because that's just how engineers talk. We talk in rectangular, we talk in polar, we do both. We have to be able to do both very comfortably. Okay? So that's just a discussion of rectangular polar. We can always multiply R1 plus JX1 times R2 plus JX2, okay? We can multiply those numbers by foiling it. We have R1, R2 plus J times, let's see, X1, R2 plus X2, sorry about that. Let me toggle back. What's going on? Huh. My machine seems to be locked up. Can you hear me still?
Yeah.
Hear you.
Yeah, I can hear you.
Sorry about that. Like my machine just wouldn't, it wasn't responding. Okay, so let's continue. So I have R1, X1 times R2. So now I have to have X2 times R1. And then the last one is plus J squared, X1, X2. What do I do now? Well, remember, J is equal to the square root of -1. J squared is equal to the square root of -1 times the square root of -1, which is equal to -1. So this becomes R1, R2 minus X1, X2 plus J. X1, R2 plus X2, R1. You can always multiply polar number or rectangular numbers, no problem. How would you divide numbers? Joanna, do you have an idea how to divide those numbers? This is a trickier one. Moses, would you like to help her?
Hello?
Would you like to help her?
To divide these two numbers.
Yeah,
Yeah, I know, there is a long equation such that, we will be at some point adding the imaginary parts and then remove. I don't have that in mind, but I can.
you're on the right track.
Yeah, I know there is I know there is an equation like that, but I don't have that in mind.
Yeah, but you're on the right track. It's very difficult. And the way that you divide complex numbers is you actually don't divide them. You multiply by the complex. Whoop. Is my screen flashing?
Nope, looks normal.
Okay, my machine like it keeps flashing back to PowerPoint, so just give me 1 minute. Like it's locked up again. Sorry. I don't know what's going on. My mouse is not working. Okay, please bear with me while I try to troubleshoot. See if I can minimize that. What happened to whiteboard? Huh. Whiteboard just crashed. Let me see if I can bring it up. Sorry about this. The whiteboard just completely crashed. Okay. So you multiply, can everybody see my screen again? You multiply by the complex conjugate. Because when you do that, this becomes and that's whoops, complex conjugate. This has to be sorry about that. This has to be negative number. So now when I have a complex number in the denominator, it's gone, right? So now you just do regular foiling and then you multiply by that. Okay. What if there was another way? So let's, before we jump into this, you see this number right here? I would like to solve for that so that I have 1 plus 2j, multiply that by, whoops, 3 plus j4, okay? So I'm going to repeat this equation over here, and I'm going to multiply those two numbers together and see if I get the results. And the way that I'm going to do that is with MATLAB. Okay, so my equation is, so R1 is equal to 1, R2 is equal to 3, X1 is equal to 2, and X2 is equal to 4. So now I'm going to go R1 times, so that's the first one, minus X1 times X2, plus J times X1 R2, plus X2 times R1. I got -5 plus 10, okay? If I did the calculations this way. Now MATLAB's pretty darn smart. I should be able to put these two numbers in directly and it should do it for us. So I'm going to go 1 plus 2j. And and multiply that by 3 plus 4. And then hopefully I get that same number. What do you know? Okay, so MATLAB probably does that. Let's take a look at another way. So the first thing I want to do is if I can convert these numbers to magnitudes and angles, right? So this right over here. Come on. This over here is R1 squared plus X1 squared. And the angle is the inverse tangent of X1 over R1. And then this number over here is R2 plus X2. Both of those are squared. And then the angle, boy, this is just really acting up on me. And I don't know what's going on. At an angle of inverse tangent of X2 over R2. So let's go ahead and do the display stuff here. So let's go back to MATLAB. And now I'm going to do the square root of R1 squared plus X1 squared, square rooted. That's 2.24. And I'm going to do the inverse tangent of X1 over R1. And I'm going to convert this to degrees. So this right here is 2.24 at an angle of 63.43. And let's do the same thing over here. But now this is going to be, why is this not working? Okay, I guess it doesn't want to. So this is going to be equal to the square root of R2 squared plus X2 squared square root. And then this is going to be the A tan of X2 divided by R2 times 180 over 5. So 5 at an angle of 53.13. Now, if I multiply those two together and do exactly what Ethan said, take the two magnitudes, multiply them together, take the angles and add those together, that should be the correct results. So I'm going to go back here into MATLAB and I'm going to multiply, let's see. I'll call it Z is going to be equal to R1 plus J times X1 times R2 plus J times X2. That's our value that we saw from before. Now I'm going to look at the magnitude of Z, 11.18. Then I'm going to look at the angle of Z, multiply that by 180 over pi. All right, so let's take 5 and multiply it by 2.24. Well, what do you know? 11.18 versus 11.2. Those numbers are almost exactly the same. Now I'm going to look at my angle, 116. So 63.43 plus 53.13 is it's almost the same number. So in summary, here's the most important part. Okay, in polar, A at an angle of theta A multiplied by B at an angle of theta B is equal to A times B, theta A plus theta B. A at an angle of theta A divided by B at an angle of theta B is equal to A over B. And these are subtracted. Okay? So when you do polar coordinates, you either multiply or divide the magnitudes, and you either add or subtract the angles. And this is an essential to how we do root locus. If you don't understand how to do this, it's going to make all our root locus math almost impossible, because what we end up doing is we add and subtract angles all the time, and then we divide magnitudes all the time. Okay. So for polar numbers, multiplication and division is a much more straightforward approach. You can do rectangular. R1 plus JX1 times R. Go ahead. Or minus. That's how you multiply. Divide is multiplying by complex conjugates. Adding or subtracting. Let's show you how to add and subtract. This is the easiest one. So when you add or subtract rectangular numbers, what you need to do is add the real parts or subtract the real parts, add the imaginary parts, or subtract the imaginary parts. Okay? Very important that we understand how to do the rectangular and polar math to make, make our work way more straightforward in root locus. Pausing to see if there are any questions. I think it was Mort who said he might have seen this in physics too. Does this ring a bell at all, Mort? Does this look kind of what you were discussed or presented with back in physics too?
Yeah, it does.
Okay.
This is starting to look. I feel like I have seen this before in some of my math classes, but I would say to you going over it is starting to I guess clear the cobwebs.
Okay. How about any of the EET students here? Did John go over this in EET 312?
I think he did.
Okay. Moses, is this covered at SMCC in the AC circuits classes or someplace else?
Yes, we went through this a little bit.
Okay. Does this ring a bell then?
Yes.
Okay. How about our friends that are Eastern Maine Community College transfers? Is this stuff that was presented to you either in the electrical program or in the math?
I don't honestly remember exactly what the way Rick was presenting to us, but those look pretty familiar to me.
Okay. Okay. Good. So it's good to get everybody on the same page, because when you're dealing with the root locus stuff, it's so important to really be able to do this complex quote unquote math. It's not hard math. It's just keeping square of it, because you'll be doing this a lot. Even when you get out in industry, when you do this, understanding how to multiply magnitudes and angles will really help you get a better understanding of what's happening. Okay. So now that hopefully everybody's sort of on the same general understanding about doing rectangular and polar, let's go back to let's go back actually to here first. So remember when I said angle of GH plus or minus at an angle of 180? So the way that you're going to do that, remember my GH is going to have a bunch of poles and zeros. And I'll just put 2. All right. So if we want to know if a particular point, a particular value of S, let's say S is equal to 3 plus J4, for example. What we need to do, this is going to be a valid point, we know that the angle GH at S equals 3 plus J4 has to equal plus or minus 180. So what you need to do is you're going to plug in 3 plus J4 plus Z1, 3 plus J4 plus Z2, 3 plus J4 plus P1, 3 plus J4 plus P2. All right, so based on what we've done so far today, is there a fast and easy way to go ahead and have an idea of how to calculate these angles? Remember, I'm looking at these angles. So this is G, but I want to go ahead now. Let's take it out of here. I want to go ahead and do these angles here. So how would you do that? And this is the key part of root locus. This is when we can simplify things. How would you calculate angles? Well, this has a magnitude and an angle. Magnitude and an angle. Magnitude and an angle. Magnitude and an angle, right? So what you're going to do is we'll just call this theta Z1. And you're going to add to it the corresponding angle that you would get for that theta Z2. And the way that you get the angle is that inverse tangent of the imaginary part over the real part. So you got the two angles in the numerator. You added them together. How do you include or take into account the angles of the denominator? Look back at the stuff that we presented today and see if there's anything that will help you. How would you include those angles that are associated with the two poles? These are polar numbers, right? Magnitudes and angles. We just drew those as magnitudes and angles. How do we include them? Well, let's step back. The two angles that I had for the zeros, where were they? In the numerator or the denominator? They're in the numerator, correct? So I multiplied two numbers that are in the numerator. I converted them to polar coordinates, and they are multiplying each other, which means I added the angles together. The two angles that I'm going to get for the poles are in the denominator, or they are dividing the two angles that I just calculated. Dividing the two angles means I subtract them. So the way that you figure out if poles are, if this S equals 3 plus J4 is a valid point, you put all those numbers in, then you calculate if this is equal to plus or minus 180. Whoop. This is equal to plus or minus 180. And if it's a valid point. If it's not equal to plus or minus 180, then it's not valid. Okay. And what we'll do is we'll start to look at angles of arrival or angles of departure based on when we either arrive at a route or depart a route, we need to know what angle that's going off at. And the angle that goes off at has to sum or has to be determined based on all the other angles in the system. They have to equal plus or minus 180. And that's where we get to here. So I'll do this last slide. I got a few more minutes. Hopefully it doesn't crash my machine. So here's our graphical representation. I want to determine S equals -3 plus J4. Here's the G of S, here's our closed loop transfer function. So we plug in S equals -3 plus J4. Every point we see an S. So this gets to be a lot of work. So what we're going to do is we're going to plug in S equals -3 plus J4 for this numerator term. And we're going to end up with a magnitude and an angle. So this is just written using Euler's identity, but you could have said square root of 20 at an angle of 117. That would have been fine. So here is magnitude and angle for S equals -3 plus J4. Now I'm going to do the same thing for S. That one's pretty easy. 5 at an angle of 127. Now I plug in my S plus 2. Then I get square root of 17, e to the j 104. And then I plug that all in over here. And now to get the magnitude, I take the square root of 20, 5, and 17. So let's do that in MATLAB. Square root of 20 divided by the square 5 times the square root of 17. And that, oops, I forgot to close parentheses. And that is the magnitude of G of S, H of S evaluated at that angle using polar coordinates. I just divided the magnitudes. To get the angles, I'm going to go ahead and go 117 degrees. I'm going to subtract from that the two terms in the denominator, 127 and 127 and 104. And I get -114. Okay. So again, this is imperative to understand how to do polar multiplication and division. So my suggestion would be spend a little bit of time seeing if you can plug in a bunch of different numbers, like try, I don't know, pick S over S plus 7 times S plus 5 and see if you can get the magnitude and the angle. Okay. Because what we end up getting, if this -3 plus 4, we get this value over here. That is the angle, -114, and the magnitude is 0.22. Don't worry super duper about what this value is, but what we're saying is to go from this point to this point, we have to go square root of 20, and the vector is 117. If we wanted to do the 0, you might be able to see it, but you can see I have to go a harder angle, and the magnitude is slightly increased. If I want to go from -2, which is over here, then I don't have to go quite as far, and my angle is not severe. So you can see I only have to rotate 104 degrees, and I'm only square root of 17. So that's shown by these. So this is the first one, the second point, and the third point gives me those values. And the sum of those is how I get that point. All right, I'm out of time. Any questions? All right, well, if no questions, have a great day. And I'll see some of you on Thursday. Take care, everyone.
Hey,